Wonderful. Hello again, everybody, and welcome on behalf of the International Tree Mortality Network. My name is Rupert Seidel, and I'm really happy to have you all here. Today with us is Joan Dudney, who's our speaker today. And I have the great pleasure of introducing Joan briefly to you before handing over the word to Joan. Joan received her BA from Occidental College in LA and then did a PhD at the University of California at Berkeley. Joan did postdocs with the Smith Fellowship at UC Davis and at the National Center for Ecological Analysis and Synthesis. And Joan is now an assistant professor of global change ecology at the UC Santa Barbara. And Joan works on a lot of exciting things, but broadly, the umbrella, I would say, is understanding the causes and consequences of global change in terrestrial ecosystems. And specifically, and this is what a lot of her talk's gonna focusing on today, disentangling the complex effects of climate change on forest communities with a focus on disturbances and how they interact and cascade and impact ecosystems. So we're gonna hear a lot about how diseases and beetles and fires all kind of come together and duke it out on the landscape, which is an exciting and often overlooked aspect, I would say, of tree mortality. I will also stress in this day and age that Joan is actively engaging in issues of diversity, equity, and inclusion, which is, I think, very important in academia. And she's an active member of a number of ecological societies. We're really happy to have you, Joan. Before I hand over the word to you, I will still say that for the audience, you can post your questions already during Joan's talk in the Q&A feature that is down at the bottom of your Zoom panel. So there's this Q&A button, and you could post your questions there. And we will then, after Joan's talk, basically select questions. I already asked for your understanding that usually we're not able to get through all the questions, but we will try to pick a diversity of questions and relate them to Joan so that Joan can answer them. So start posting questions already as you have them, as Joan gives her talk, and then we will get to those questions at the end of the session. Wonderful. With that, without further ado, Joan, it's really lovely to have you here. Thanks for making time. Thanks for being here. And we very much look forward to your input. Floor is all yours. And you're still
Start by sharing my screen.
Yes, go ahead. Thank you.
Are we in business? Ready to go?
Yes, looks wonderful. Good to go.
Okay. Well, thank you so much for that wonderful introduction, Rupert, and thank you for inviting me here today to speak. I'm really excited to share some of this research and synthesis that I have been working on with some amazing colleagues, including Julie Edwards, Brian Harvey, and Rupert Seidel. So why study disturbance interactions? Forest disturbances often don't emerge in isolation, and they can overlap in space and time, sometimes leading to these really surprising outcomes on forest ecosystems. So this is an example of the interaction between drought and fire drought and bark beetles in Sequoia Kings Canyon National Parks from California. This was taken in 2015, and this was a particularly surprising event. I was working with park managers and scientists who'd been there for over 30 years. They had never seen this type of mortality event ever. And so it's really sort of encapsulating how these interactions can really lead to these sort of nonlinear surprise outcomes. But there are other examples where disturbances can interact to dampen outcomes. So for example, fire effects on disease in Yosemite National Park has actually led to disease suppression in some areas. And this is some recent research that my grad student, Michelle Moore, has been developing. Under climate change, we are increasingly observing more frequent and severe disturbances, as well as an increase in the impacts of their interactions. And that these are as I mentioned, in some cases leading to these really unprecedented mortality events. So though these disturbance interactions are clearly very critical to understand, given their impact, they remain poorly understood for a number of reasons. First, disturbance interactions are often relatively rare in ecosystems, and many studies are retrospective, which can bias results. Second, interaction effects of disturbances are often difficult to measure. They sometimes require 16 times the sample size of a direct effect, and this can be completely unattainable given the logistical challenges that we're often confronting as field scientists in forest ecosystems. Third, disturbance interactions are totally complex. They involve many different mechanisms, and this can really complicate prediction, particularly under climate change. And then finally, forest disturbances are often studied in isolation in subdisciplines like fire ecology or entomology. And so we often lack a more holistic understanding of how these different disturbances might influence each other. Given that we know so little, we know some things, of course, but relatively little about disturbance interactions, as a result, we understand even less how climate change might be shifting or modifying these relationships. So that's ultimately what my talk will be about today, understanding how climate change is and will continue to shift disturbances and their interactions. To answer this question, how is climate change shifting disturbance interactions, my colleagues and I conducted a systematic review of the literature. And we ended up using the AI platform Elicit that uses semantic scholar literature database to parse the thousands of potential studies that might have been related to disturbance interactions. From this first broad search, we filtered papers based on their focal disturbance agents, whether they discuss climate change effects, and we ended up with over 450 abstracts that from which we ultimately read 164 papers. But during this review process, we actually hit a pretty major roadblock. We discovered that the literature did not agree on our fundamental premise, which is what a disturbance interaction even is, which made our task of understanding how climate change might be affecting these relationships even more challenging. So just to give you an example of some of the discrepancies in the literature, some have described disturbance interactions as the alteration of one disturbance by a previous or co-occurring disturbance, which is very similar to how we might describe a linked disturbance, which is when a disturbance may interact with another by changing its extent, severity, or probability of occurrence. Some have separately defined direct and indirect interactions. So indirect interactions, for example, are those mediated through ecosystem state variables, such as composition or fuel. Still others describe how disturbances can interact to affect the environment. Some disturbances may be synergistic, not only additive. So there are a lot of different ways that we think about defining disturbance interactions, as well as the many other types of effects that we might include in interactions and disturbance interactions. And this variability in the literature has been identified by a number of thoughtful authors that have developed these wonderful frameworks to describe how these terms might be related to each other. But these frameworks also don't necessarily agree with each other. So this framework on the left here is really describing how one disturbance might affect another disturbance, more like that linked disturbance definition that I previously mentioned, where this framework on the right is really trying to understand how disturbance A and B might interact to shift an ecosystem attribute, resilience, or resistance. Ultimately, these differences reflect how we broadly think about interactions as ecologists versus interaction effects defined in mathematical models. So for example, I think ecology is, broadly interested in understanding how organisms interact with each other and the environment. And so in this case, we're capturing a ton of different types of effects that are all under this umbrella term of interaction. And this contrasts with mathematically defined interaction effects, where direct effect on an explanatory variable depends on the level of another explanatory variable. This requires 3 variables, 2 explanatory variables and an outcome variable at minimum. So because these 2 definitions are describing very different types of effects, we can sometimes be comparing apples to oranges. And that can be pretty problematic if we're trying to summarize the literature on disturbance effects. What it means is that we have a hard time understanding how climate change might be affecting these relationships if we don't agree on what those relationships are in the first place. And it's really hard to form generalities across different types of ecosystems and across scales. So clearly, at this point, our next step was to develop a typology where we would try to reconcile these differences and move forward with this new typology and organize the literature and studies based on what we've developed. But how do we reconcile these differences in a way that's more defensible than we got together, discussed these frameworks, and we think this is the right definition? I think a more defensible approach is to ground our definitions and typology using mathematical equations and a deep understanding of the mechanisms driving outcomes that we're observing. I've recently been applying concepts and approaches from the causal inference literature in my research because some of these approaches, including directed acyclic graphs, have really helped me parse a lot of this complexity. So using the same approach, we developed our typology by identifying the underlying effects and mechanisms that lead to disturbance interactions. And then we distinguished and classified these relationships using a causal pathway analysis. So today I'll be focused on the process by which we developed this unifying typology. I'll apply and ground this approach using a case study from the Sierra Nevada. I'll then highlight how we can use this framework to understand climate change effects, and then finally discuss a little bit about future directions for this focal area. So to develop our typology, we use directed acyclic graphs here on the left, as well as the literature, which has done an amazing job over the years of identifying these important causal relationships, using, in some cases, these wonderful heuristics like the fire and disease triangles, which really help isolate what are the most important factors that lead to disturbances as well as their interactions. DAGs have really become a mainstay in my research because they help illustrate in these very simple terms how variables influence each other. This approach, it forces directionality, which can feel really uncomfortable as ecologists because we all know that there's often bidirectionality in these relationships, A affects B and B affects A. But what it does is it forces us to think exactly precisely how in time these relationships might be affecting each other, what comes first and what follows. It's this very reductionist first principles approach to understanding these relationships, which is helpful because we have a ton of different ways that we describe these effects, including linked interactions, cross-scale interactions, compound disturbances, network effects, disturbance interactions, and the list goes on. I don't have time to go into how we defined all of these different disturbance effects, but rather I'll just focus on the difference largely between linked disturbance interactions and disturbance interactions. So let's think about a forest that experiences disturbance from bark beetles and fire, which affect tree mortality. The most basic way we can model their effects on tree mortality is through a linear model with their additive effects. So I'm including the direct effect of fire and bark beetles on the probability of tree mortality. This, by the way, is just one example of an additive disturbance effect. We could include in our outcome variable a forest metric, another disturbance. An additive effect is just when 2 disturbances add to affect an outcome. Now let's imagine a bark beetle outbreak affecting 2 trees, one that has been moderately burned and another that remains unburned. Which tree is more likely to die? the tree that was impacted by fire and bark beetles, or just bark beetles? You're right. It would be the tree that has been burned and attacked by bark beetles. And that is what an interaction effect is capturing. And we can draw this by drawing a directional arrow that bisects the path from beetles to mortality. DAG's force directionality. In reality, a lot of these models are estimating these effects simultaneously and bidirectionally. So ultimately, this arrow is describing that this interaction term is modifying the relationship between bark beetles and mortality. These disturbance interactions are capturing very different effects than linked disturbance effects shown here, where bark beetles are directly affecting fire, which can be modeled using this very simple sort of conceptual linear model where bark beetles affects the probability of fire. These bark beetle effects can result in shifts in fire extent, duration, frequency, severity, or timing, and are, again, different effects from our interaction effects, right? So this is where the effect of one disturbance influences another disturbance's behavior, and they can include direct and indirect effects, but not feedbacks, which I'll get into the next section. In contrast, these disturbance interaction effects are when the effect of one disturbance on an outcome variable depends on the level of another disturbance. So using this framework and approach, we developed this typology where we defined 7 distinct types of effects. I won't go into this in detail today, but just to show you that we use this sort of same approach to think about how a lot of different types of effects that can emerge between disturbances. So now I'm going to take you to one of my favorite places in the world to talk about a case study. And this is the Sierra Nevada. It's, I think, an ideal study system for understanding disturbance interactions under climate change because of this amazing white pine system that we have, which spans a really strong elevational gradient. I've been studying forest disturbances in these systems for almost 12 years. And other than, of course, the incredible awe-inspiring beauty, I have learned so much about how these disturbances relate to each other because of this really unique study system. Starting at low elevations, these are where we have our mixed conifer forests. And this system houses our sugar pine, which is one of the largest pines in the world, and it's just a magnificent tree species. In the montane zones, this is where we have our western white pine, which is slightly smaller than sugar pine. And then finally, higher up in our subalpine to treeline zones, we actually have 3 different species of white pines: limber pine, foxtail pine, and white bark pine. What's unique about the white pine system is that they are all influenced by these disturbance agents, by the same disturbance agents, including this tree disease, white pine blister rust, which is shown here with the Acacia spores on the white pine host. And it is often a lethal pathogen. It can travel for hundreds of kilometers on wind currents. It's invasive, so originally it was from Northeast Asia, and it has contributed to precipitous declines in a number of white pine species in the US. White pine blister rust co-occurs with these other disturbance agents, including mountain pine beetle and drought. And it's because of the combination of these drivers that white bark pine, our subalpine tree species in the West, has declined so much it was listed recently as threatened under the Endangered Species Act. So some of the data that I'm presenting on today come from a study where I led a resurvey of 154 plots that were placed throughout this national park, Sequoia Kings. To get out to these sites, we had to travel for multiple days off trail. These were randomly placed plots, and so we had to go everywhere, and that was incredibly remote and incredibly beautiful. So one of my favorite research projects that I've ever participated in. What was also super fun was that, and very challenging, we were given these old notes that the original surveyors had left for us, which would describe how to find a plot. And it would usually be a rock with some sort of dimension. And we're looking up at a mountainside of rocks thinking there's no way we're going to locate this quarter-sized metal marker that was drilled into this rock, 20 years ago. But amazingly, we were able to relocate all of these plots, and it gave us a lot of this amazing long-term data and insights into how these disturbances are changing through time. So these disturbances can be sort of illustrated and their relationships illustrated in a lot of different ways. We show here on the left additive effects where we have drought and bark beetles adding to affect white pine blisterus. You can have cascading effects where one disturbance affects another disturbance, which affects a third disturbance or another sort of forest metric. And then finally, these linked disturbance effects where one disturbance is affecting another disturbance. And I'm just going to focus on thinking through how does drought affect white pine blisterus in this system? Well, I think where we really start seeing differences between these effects is by identifying their mechanisms. So one of the important mechanisms that in which drought will affect disease is by increasing water stress, which can lead to stomatal closure. And so this is some data that I collected between 2012 and 2017, which spanned some drought years and basically showed that drought typically leads to increases in water use efficiency, which typically is associated with stomatal closure. And that ultimately is not great for the disease because the white pine blisterus infects through needle stomata. So during drought, the probability of infection actually can decline, particularly in drought-stressed trees. We also know from the literature that white pine blisterus requires high humidity for reproduction. So hot, dry conditions during drought can lead to the desiccation of spores and limit reproduction, which is also negative for disease. And by the way, this we would consider a direct effect, whereas the first effect, stomatal closure, would be an indirect effect because it's mediated through the effect of drought on trees. And then finally, drought can also remove hosts as well as their infections, both of which are not great for disease prevalence. The net effect on drought is ultimately what contributed to decline in disease prevalence at low elevations between surveys, and this figure shows the elevation terciles on the x-axis and difference in disease prevalence on the y-axis. And in these low elevations where drought frequency intensity is highest, that's where we saw the largest declines in disease prevalence over the years. So now let's switch gears a little bit. So that was the linked effect of drought on disease. And now let's think about how drought might interact with disease to affect tree mortality. These interaction effects, which again, we can show using an arrow that bisects the effect of white pine blisterus on tree mortality. Ultimately, there are three major mechanisms by which trees die following the impact of a disturbance agent. These disturbances can increase carbon starvation, hydraulic failure, or physical damage, and sufficient enough where the tree no longer can recover. White pine blisterus largely causes tree mortality through carbon starvation and hydraulic failure, recognizing, of course, that these pathways do interact as well, which further complicates our understanding. But ultimately, they're acting primarily through the effect on mortality is primarily through these two mechanistic pathways. And that's also the same for drought. Drought, of course, is leading to increases in likelihood of carbon starvation and hydraulic failure. And so it makes complete sense given that both of these disturbance agents are causing mortality via the same mechanistic pathways, that they would also be interacting with each other to amplify each other's effects, right? So here we're showing that drought is bisecting, it's interacting with the effect of disease on tree mortality, likely because it's pushing trees that are infected with disease closer to these mortality thresholds. And so we see this sort of amplifying nonlinear effect of drought and disease on tree mortality, which is that classic interaction effect. And from the data that I collected, I was able to show that, this is likely happening given that trees over here on the right that were infected with blister rust during drought were much more likely to die, which is sort of that classic, again, interaction effect. So my hope is, now that we've sort of gone through both of these mechanistic pathways of how these disturbances are affecting each other, as well as mortality, that we can clearly distinguish now the difference between these sort of direct linked effects of disturbances on other disturbances versus these interaction effects, where disturbances are interacting to amplify or dampen the outcome variable. And this is just one example. There's a lot of different ways that all of these relationships can be estimated. And there's a lot of different outcome variables that we might want to estimate. But for now, we're just applying this sort of case study example to sort of highlight how using this sort of mechanistic approach and these DAGs can really help us understand what the differences are really between these different types of effects, right? So that we know that interaction effects do not include how drought might increase or decrease the probability of disease. And in these linked effects do not include the interaction between drought and disease on tree mortality. Ultimately, however, we do need to understand and quantify both of these effects if we want to understand how climate change is impacting these relationships and changing patterns of disturbance as well as their effects on tree mortality. To do this well, however, I think requires a pretty big advance in how we're thinking about quantifying and measuring these effects, probably through ideally experimentation or very careful causal inference analysis. So I think this sort of highlights a couple of important implications for interpretation of these effects. First, I think we want to be really precise in the questions that we're asking and associating those questions with really careful research designs. I think using DAGs can really help clarify the exact type of effect that we're capturing so we can interpret our results really clearly. I also think that long-term studies are really critical to accurately capture all of these different mechanisms that might be affecting our outcome variables. If we have short-term studies, they might not capture, these interactions with other disturbance agents, some lagged effects that can emerge in these studies. And so I think making sure as much as we can that we're going back and we are constantly monitoring these systems and doing these long-term studies, I think will greatly enhance our ability to estimate and understand these effects. And then finally, I think there's a lot of different functional forms that can emerge and are sort of best capture how these disturbances are interacting with each other, which complicates prediction, but ultimately helps prediction if we identify these functional forms correctly. So for example, lagged effects are fairly common in disturbance interactions. Bark beetle effects on fire, are often initially positive, but then become negative as decomposition rates increase. Nonlinear effects can lead to both positive and negative effects of disturbances on each other. And then finally, feedbacks can lead to pretty surprising outcomes, particularly under climate change, as they can completely shift the sort of direction and magnitude of disturbance effects. So now going back to the literature and our literature review, what does the literature say about these linked and interaction effects? Well, ultimately, what we're primarily doing today is focusing on these linked disturbance effects. There are fewer studies that are really differentiating between linked disturbance and interaction effects and how they might be changing under climate change. We're often focused on, maybe one or two mechanistic pathways that these disturbances might influence each other. And I think that can overlook some important effects. And I think more holistic approaches will help reduce the bias associated with that. I think what we found is the majority of studies report positive effects of one disturbance on another, but negative effects do often occur, perhaps more frequently than we appreciate. Which now brings me to the moment of truth. Can we use this approach and our typology to better understand how climate change is affecting disturbance interactions? Well, let's find out. Because I love DAGs, we're gonna continue with our DAG push. And I'm just going to give you a few conceptual diagrams to highlight the important ways that climate change can modify these relationships. So in the Western US, the probability of high severity fire is on average positive, right? It's often positive in a lot of different systems. So even without bark beetles in the system, the probability of high severity fire is generally positive. And if you add bark beetles into the system, now the probability of high severity fire is often higher depending on sort of the time scale at which you're estimating this effect. Under climate change, the probability of high severity fire can be amplified, it can be dampened, or it can experience no change. These are sort of the possible outcomes in which climate change might be shifting these relationships. So because bark beetles are often, positively associated with warming temperatures, or in general, we see greater reproduction during warmer periods, we would expect that average increases in temperature would lead to increases in bark beetle populations. And this increase in bark beetle populations would ultimately lead to an increase, an amplified effect on the probability of high fire severity, or high severity fire. And I think what's useful and important to note here is that this linked effect remains constant, right? Because if we have truly identified the causal relationship between bark beetles and fire, that relationship will not change because of climate change unless there is an interaction effect. But that direct effect, that direct linked effect, if we've causally identified it, is going to stay the same through time. What will change are the amount of bark beetles in the system. So it's really the increase in bark beetle populations that is leading to this amplification of the probability of high severity fire. It's not that the effect of bark beetles on fire is increasing because of climate change. I think that's an important distinction to make as we're thinking particularly about prediction, but also as we're thinking about understanding the difference between these interaction effects and these linked effects. So now let's think about how, temperatures might be moderating, which is another way of saying interacting with bark beetles to influence fire. So here I've drawn that climate change is increasing average temperatures. Both temperature has a positive effect on bark beetles. And in this sort of conceptual diagram, we hypothesize that temperatures also interact with bark beetles to amplify the effect of fire. So here, in this circumstance, we would expect potentially a super amplification of the probability of high severity fire, because now not only are bark beetles increasing in the system, which is increasing the probability of high severity fire, but there's also this interaction effect that is leading to these sort of nonlinear effects of bark beetles on effects on fire, so nonlinear effects of the outcome of high severity fire, which means that we can get these super amplifying effects under climate change. And I think this is probably what we should be most concerned about, given that, many of these disturbances, all of these disturbances to some degree cause tree mortality. So in the literature, the effect of climate change has been documented or discussed, but where the sort of evidence is strongest is the sort of link relationship between drought and fire, particularly in the Western US, where climate change is increasing the frequency and severity of drought, which is increasing the extent and frequency of fire. The attribution in these studies is extremely strong, and we are able to, using these rigorous approaches, we can actually create these sort of counterfactuals and really isolate the effect of climate change on these systems. Many studies are still focusing on these amplifying positive effects of climate change, but amplified negative effects as well as nonlinear and lagged effects can lead to high variability in the net effect of climate change on disturbances and their interactions. So fire effects, for example, on disease can be negative, leading to greater disease suppression where fire frequency and severity increases. One of the most well-studied and well-understood fire disease linked interaction effects is between sudden oak death and fire in the West. And this is sudden fire often removes hosts, which ultimately suppresses disease pressure in that region. So with increase, so there's somewhat of a sort of positive outcome here if we're thinking about managing particularly invasive tree diseases under climate change. Additionally, fire effects on bark beetles can also be nonlinear and negative. For example, high severity fire reduces bark beetle outbreaks by eliminating their hosts. So if we have higher frequency and severity of fire, that actually ultimately can reduce bark beetle outbreaks at certain patch scales. So these sort of nonlinear and negative effects, I think, are really important relationships to understand and quantify when we're thinking about, particularly when we're thinking about how climate change might be shifting these relationships. And I'm going to take you back to Sequoia Kings again, because this system also is sort of rife with nonlinear relationships that lead to these really interesting complex outcomes. And I'll just briefly go through this. So here, this is a figure showing the probability of being affected by white pine blisterus across this really strong climate gradient that captures all or 4 different white pine hosts here. And you can see that that relationship is nonlinear. I'm showing elevation here, but ultimately the relationship with temperature, which is highly correlated with elevation, is nonlinear, which means that as climate change is shifting where the disease emerges, it's going to have both positive and negative effects on disease prevalence in space. And the effect of meteorological drought in the system is also nonlinear. So drought leads to, as we saw earlier, reductions in infections and low elevation in warm regions. But actually at high elevation, meteorological drought can actually extend the growing season, which can increase the probability of infection because stomata now are often open for longer into the fall season, which is exactly when white pine blisterus spreads to infect white pine hosts. And so we have this sort of nonlinear effect of drought. We have this nonlinear effect of temperature. And this drought effect is somewhat going to be lagged under climate change. So it's going to become increasingly more important as climate change continues to warm these high elevation systems. So initially we might see overall disease declines as we have seen in the system, but ultimately in the long term, climate warming will accelerate the rate of spread at high elevations. So again, sort of highlighting that these nonlinear relationships are probably very important for a lot of different systems. They can lead to these really complex outcomes, But if we think them through and we can identify them well, this is best identified, I think, a lot of them using these really strong climate gradients, we can much better understand and predict how climate change will be shifting both linked disturbances as well as the interactions between disturbances. So in summary, I hope you now agree that it's really important to distinguish between different types of effects. I think what we are measuring and how we are interpreting them, how we are interpreting the effects and the results of our studies is really important especially if we're wanting to understand broadly how climate change is affecting these systems. First of all, being more precise with the terminology, I think, can really help. And that, I think, can also be leveraged using these sort of causal inference approaches, which really force us to think about what the precise cause of the effect actually is, not just sort of thinking more about these sort of kitchen soup models where we're throwing in a lot of variables and sort of looking at whether or not they are significant. I think we need to focus in general a lot more on less well-studied interactions. So we have pretty good understanding of how bark beetles and fire interact with each other. We have a fairly good understanding of how drought and fire interact with each other. We know much less about how disease and fire and disease and bark beetles and disease and wind in general. Ice storm, there's a lot of disturbance agents that are also impacting these systems that are also changing because of climate change, but we know very little about how those disturbances might shape forest outcomes in the future. I also think it's important to develop a predictive framework and really dive for this. This is just sort of a first pass differentiating these two types of effects. We know very little about when two disturbances might interact versus when, disturbances just directly affect each other. And I think we really want to know why it is that some disturbances interact to amplify or dampen outcomes, right, with that interaction effect, versus when disturbances are simply, directly affecting one disturbance's behavior versus another disturbance. This is sort of like a frontier, I would say, for ecology, understanding why we see interaction effects in the first place. And I think that's super important if we're wanting to understand where these disturbances might lead to the greatest mortality under climate change. This idea of this super amplification, I think, is really scary and really important. And right now, we're not really differentiating interaction and linked effects well. And so we probably don't have a good idea of where the super amplification is very likely. And then finally, I didn't have time today to really go into feedbacks, but feedbacks are so important, and they ultimately, a lot of times, lead to dampening effects. There are these positive feedbacks that often lead to a disturbance outbreak and the big impacts that we see on forests. But then there are often these negative feedbacks that ultimately stabilize the forest ecosystem following disturbance. And those negative feedbacks can actually interact and influence other disturbances, which is very complex and represents another frontier for this literature, but I think really are important to understand if we're thinking about predicting how climate change might be shaping and shifting these relationships. Ultimately, I think for a lot of forest ecosystems that are controlled by disturbances that typically require a certain, density of fuels or a certain type of fuels or just type of disturbances or specific species in the case of disease, we might actually see declines, these big increases in mortality, but and the sort of frequency and severity of disturbances, but then ultimately these could potentially decline in some regions where we simply are running out of vegetation that's suitable for these disturbances to emerge in the first place. So with that, I would like to thank my wonderful colleagues, Julie Edwards, Brian Harvey, Rupert Seidel, who helped me think through a lot of these complex relationships. And I will take any questions.
Thanks, Joan. That was a really wonderful seminar, really exciting stuff. We don't have it set so that the participants can, vocally applaud for you, but I'm sure that they are doing what Rupert, Adriani, and myself are. We have several questions already from the audience that have been posted. As a reminder, as we're going through and answering these questions, do use the Q&A function here in Zoom. It's down at the bottom near like the share and participants buttons. And through there, we'll try and organize and ask these questions as they come up. So to kind of get started, near the beginning, Joan told us about the systematic literature review that was done. This question comes from Ben Bon-Lamberti, who says, "Great talk. Any takeaways from your experience using an AI research assistant? Did it accelerate your science, provide a useful test or learning experience, or something else?" I think we're all probably curious about this.
Yeah, the reason why we ended up going in that direction was because the Web of Science was just untenable in terms of the number of papers that it identified that could potentially be linked or discussing this broader topic that we were interested in reviewing. And we simply did not have capacity given the deadline of this paper. And Elicit really helped filter out. That was, I think, the major benefit of using this AI platform, was that it allowed us to filter out a lot of those studies that we would have otherwise filtered, but that would have taken weeks and weeks to do in a matter of minutes. And so it identified, I think, the most critical papers that were relevant to our topic. And then from there, we actually needed to filter more. I think some of the drawbacks are that, it's only using one search database. So we're probably missing literature. And it had these initially what I thought were going to be these really cool products where it could actually read through the PDF and spit out answers and sort of answer a lot of our questions, but it did make mistakes, and we ended up going in a sort of different direction ultimately with our review. So that was not helpful, but what was helpful was that we actually had a sort of an approachable systematic review process versus something that would have been totally overwhelming.
Cool, thanks for that. This is a topic that I think everybody's grappling with at the moment, is how and when and to what use these tools can be applied. Thanks also, Ben, for that question. Our next question is from Charlotte Malmborg, who says, "I noticed a lot of the equations connecting two interacting disturbances assume linear relationships. Do you think that this is a good assumption for most of these interactions, or maybe that some types of interactions or different agents may exhibit more nonlinear responses?"
That's a really great question. And I would imagine that if you're talking about, first of all, if you're talking about an interaction effect where two variables interact to affect a third variable, that implies a nonlinear relationship. But if you're just talking about the direct effect of one disturbance on another disturbance, whether it's linear or nonlinear, my sort of gut is that we probably are more on really long time scales or large spatial scales. We probably do see nonlinear effects. A lot of our field studies, though, are sort of regionally constrained, and we're often not capturing enough variation in our outcome variables or observational variables to really detect those nonlinearities well.
Cool, thank you, Joan. The next one here comes from Rudiger Groth, who asks, "What about multiple occurrences of one or more disturbances within a certain space and time? Do they change the cause-effect relationship? And have you seen any examples of this in your review?"
There's very few studies on cascading disturbances. So where you have more than two disturbances affecting an outcome, maybe a force metric or even another disturbance. Ultimately, though, the underlying causal relationship should not be changing in response to an addition of another disturbance variable, right? Like the idea of causal inference is that we are identifying the underlying relationship between two variables, regardless of whether other variables are added into our models. And in fact, that is something that if we do add other variables, for example, into our models and it changes our coefficient, typically what that's showing is that we have a biased estimate of our variable of interest, and we have not included important controlling variables. So that's typically like a bad sign for estimation if we're seeing a lot of change in our coefficients when we add new variables into the system. Ultimately, we should not see changes in our betas. If we have actually identified causal effects of one disturbance on another disturbance, or one disturbance on another disturbance on another disturbance in a cascade, those relationships will remain constant. What will change is just the sort of the amount of that disturbance, or the number of beetles in the system, or the amount of disease, the prevalence of disease. That's what's going to change, not the underlying causal relationship between those agents.
Awesome. Thank you for expanding on that, Joan. Our next question, and thank you all also to the audience. We're getting like so many great questions. I don't know if we'll be able to get to them all, but we're doing our best here. Is from Rahul Kashyap, who asks, how do you segregate out the impacts of various disturbance? How about the legacy effects of various disturbances and the temporal variability in the occurrence of various disturbances?
Yeah, that's a really great question. Lagged effects are like, when your explanatory variable changes, the sort of strength of your explanatory variable changes through time because of another effect on the system. And I think you can estimate those effects and test for those effects if you have these long-term data, right, where you can actually estimate using either sort of like a standard lagged model, or you can use like a dynamic lagged model where you're actually looking for those sort of nonlinearities through time, really precisely estimate how that coefficient on that variable, like let's say beetles, changes through time. So if you have long-term data, you can start to disentangle those, or estimate really what the lagged effects actually are and how influential they are in terms of understanding the overall effect of, let's say, bark beetles on fire. Yeah.
Cool. Thank you, Joan. Really, your talk was very interesting, and your case studies were in natural systems. We have a question here from Sebastian Ferrier from Uruguay, who says, congratulations for the excellent work and presentation. I am Sebastian from Uruguay, and here's my question. Could this approach be used in estimating the potential impact of climate change in commercial plantations, so like managed forests, in order to be added as a selection driver in genetic material improvement programs?
Maybe I'm not totally clear on the question in terms of what approach he's referring to, but I think you can use causal inference anywhere.
Yeah. I think basically the concept of these same pressures, disease, other biotic agents like insects, and of course the climatic disturbances are all common in managed and working forests like they are natural ones.
Yeah. Absolutely. I think that those disturbance agents are likely to affect any forest where those disturbances fall, where the climatic niche essentially is suitable for those disturbances. So yes, in managed forests, we're very likely to see these disturbances as well as interactions, and that can increase under climate change. So yeah, I think there's some important work that can be done in managed systems as well.
Cool. Thanks. I'm going to be selfish for a second and ask one of my own questions next. So I'll be a little self-indulgent. I thought that this, causal inference that you're putting forward is a really interesting and powerful tool, especially when we know the mechanisms to put into this directed acyclic graph. You mentioned a bit about the importance of knowing the mechanisms and that missing mechanisms could be a problem. To what extent can this approach be used to help us identify mechanisms that are missing? I think about things like the effect of temperature on some of the disturbances you presented indirectly, but then of course there can be probably really direct effects of temperature on, the pathogen, the beetle, and the tree, for example.
Yeah. That's a really good question. Identification of mechanisms, I think, is hard. This is more a tool that can help us isolate our relationships once we've gone out and measured them, right? Where we actually have the observed variables, we came up with our hypothesis and we went out and tested it. So it's more sort of conceptual in that it's enabling us to identify what we hypothesize these mechanisms would be and how they might cause outcomes. I think it's a little bit harder to use this approach to potentially identify missing mechanisms, what we could be potentially overlooking. That I think requires deep thought about looking at the literature, really understanding our system, coming up with our own hypotheses as to what might be missing. So unfortunately, I don't think it's going to solve that issue necessarily, but it will help you isolate precisely and accurately what the underlying what that mechanistic effect actually is.
Awesome. Thanks, Joan. So I'm going to ask you a final question here because we're getting really close to the end of time. Thank you for playing 20 questions with us at the end of your seminar. You've been a really wonderful seminar host seminar deliverer here today. So this question is from Sam Osborne, who states, mega herbivores are now extinct in North and South America and Europe and greatly reduced and fragmented in Africa and Asia. Herbivory was a historic and consistent disturbance to all vegetation, and it determined the structure and dynamics of forests, by providing openness. Are there any plans to include mega herbivore disturbances in your review or work?
That's a really great question. All of these were great questions. Thank you for these questions. At the moment, no, but it is absolutely true. I completely agree with Sam that this is an overlooked factor and an overlooked important component of forests, and they're just part of disturbances effects. They might be interacting with other disturbances too, and so I think there's definitely some work that needs to be done to understand what those effects are globally, but also what the effect is of losing those herbivores on these forests. So yeah, that's a great sort of future direction idea for this work.
Cool. Thanks, Joan. Yeah, last month I was in South Africa for the first time and surprised to learn that elephants were the key driver of tree mortality. So certainly a really relevant question still in parts of the world. And so with that, I just want to thank you, the International Tree Mortality Network on behalf of myself, Rupert, Adriani, and those that are also in attendance. Thank you to all of the attendees for showing up and asking these wonderful questions. Thanks most of all, Joan, to you for delivering this engaging seminar and talk and interaction through the question and answers on your very important and timely research. We look forward to seeing the paper and what lies ahead for you.
Wonderful. Well, thank you so much for having me. And feel free to reach out, anybody, if you have further questions. I look forward to more discussions about this.
All right. Take care. Bye-bye.
See ya.
Bye, everyone.